Hey everyone, this will be the introduction and safety training for CNC routing at AAP, CNC milling. We're just going to go over the process, how you can get signed up to use the machines, a general overview of the equipment, what some of their different parts are and how they work, what materials you can and can't use. We'll go over programming the machines, 2-axis and 3-axis operations, a little bit of intro to the tooling for the machines, and what some of the restrictions and potential safety issues are with setting up the machine, securing your material, and operating the machine or watching the machine as it operates. So AAP has two 3-axis CNC routers. So these are a staff-assisted resource. So unlike the laser cutters, where you sort of sign up on your own and come into the lab and use them, you will need to work with a staff person to access these machines. Time on the machine is free, but materials must be provided by the user. When intending to use the CNC router, you will sign up using our appointment system. If you're using it for the first time especially, you can always drop by the lab and talk to one of the staff people in the lab and just sort of run through the process with us quickly. But the appointment gives us an hour of time to sit down, either go over what you're trying to do and try to develop a plan, or specifically to look at a file that you have and generate the programming. So appointments can be made through our website here, and this is the same website that we use to schedule the laser cutters. So a traditional woodshop uses a handheld router. Sometimes these are also mounted to a table and table routers. What we're looking at here is a picture of a handheld router assembly. So with this tool, the router motor is attached to a base or to a table of some kind. In the case that we're looking at here with the hand router assembly, it's attached to a base. So we have the router motor here on the right, the base on the left of the image. So the router is, in theory, is similar to the drill press in that, in the way that it works, in that we have a spindle and there's a little collet on the end of the spindle, and we use that to attach cylindrical tools similar to a drill bit. With the router, the tools are like a drill bit. They're in that they're round in profile, but they are slightly different. The cutting edge is angled slightly so that we can cut laterally through material with a router bit, whereas a drill bit just drills straight in and out of a piece of material. Router bits have more function because they can cut laterally through a material. So the CNC router is basically a computer-controlled adaptation of the traditional router. So if we look at the CNC machines, and this is a picture of one of our machines. The router motor is right on the front there, and one thing you might notice is it's a much larger motor, and so this is an industrial machine, and it's it's sized really to be able to cut quickly and to run for extended periods of time. So that router motor is attached to the mast of the machine, and on top of the mast is the Z servo, and so that's a little servo motor that receives a computer control signal from the control cabinet, and that drives the Z-axis motions of the machine. The mast is attached to the gantry that bridges over top of the table, and on the left of the gantry there is the X servo, which drives the X-axis left and right motions of the machine. Finally, down on the bottom, if you look at the left lower left hand corner of the image, there is the Y servo motor. There's one on each side of the machine, and they drive the Y-axis motion of the machine. Both machines have a cutting area of 48 by 96 inches. So that's 4 by 8 feet, which is a standard size of sheet goods, sheet materials such as plywood, OSB, that you would buy at a lumber yard or at your Lowe's or Home Depot. So we refer to the cutting area as the bed or table, and sometimes we will also call this the spoil board. On top of the table is a wooden board, and when we cut out parts on the CNC machine, we end up cutting slightly through the material, so we go a bit below the bottom of the material and into the spoil board. And so this spoil board gets cut into over time and eventually resurfaced and eventually replaced. So that's why it's called the spoil board. Starting to situate yourself in Rhino. So if we were in top view in Rhino, when we're looking at the machine, the front left corner of the machine is 0, 0, 0. It's our 0 point in Rhino. Some of the materials that you can cut, we have wood, any type of natural wood, plywood, OSB. This can include hardwood. We cut a lot of foam. You can get extruded polystyrene as low cost and readily available. You can also get high density polyurethane foams that are a little bit more expensive but machine a little better than the polystyrene. We can cut plastics, acrylic, PVC, nylon, HDPE. Some of the plastics that you can't cut on the laser cutter, you can cut with the CNC. We also cut plaster, so we usually have 1 or 2 classes that are doing slip casting molds, and they will cut plaster blocks, plaster molds. We can also do soft metals, so non-ferrous metals such as aluminum, brass, and copper. We do just give a heads up that these can be very time intensive. The cutting of metal is a lot slower, 10 times slower in some cases than cutting wood. There also can be a lot of heat buildup, which can create, can lead to tools breaking. So you may need to provide your own material for cooling the tools, and also provide your own tooling if you're going to be cutting metals, especially a lot of metals. Some of the materials that you cannot cut, for wood, we don't want treated lumber. Just like in the shop, they're chemically treated, and we don't want to process those materials indoors. Fiber boards such as MDF, they have a high glue content, and there is formaldehyde in that glue, which can be irritating when cutting a lot of that indoors, even with our dust collection system. The machines cannot process stone or concrete, and we cannot do steel or stainless steel, any ferrous metals. The cutting process will generate a lot of dust and debris. So if you look at the image here, you'll see on the left we have a picture of our dust collector. So the dust collector has a length of hose that is routed over to the CNC machine, and it attaches to the mast of the machine, and ultimately down to a part of the machine that we call the dust boot. So looking at a close-up of the dust boot, so the dust boot does stick out in front of the router motor, and so this can get in the way of certain operations, and it is pulled into the equation when we try to figure out how to orient your parts, and how we're securing your parts. The dust boot can move up and down. So if it's needed, we may raise the boot during parts of your operations or all of your operations to avoid the boot colliding with your material. So this would be an image in the raised position. So if we look at it moving, you can see it raising up and down there. We want to generally keep it lowered because it will collect more dust when it's lowered, which leaves us less cleanup at the end of our job. Now we're going to talk about some of the ways that you can secure your parts while you're cutting them. So this image here is a close-up of the spoil board, the top of the machine. If we were to lift that spoil board up, you will see that underneath it is an aluminum bed, and this has a grid cut into it, and within that grid are these circular openings, and these are PVC pipes that attach back to a strong vacuum system. So that vacuum system draws air against the spoil board and sucks it down to the aluminum bed. It then draws air through the spoil board and will suck down anything that we put on top of the spoil board. This is most effective when we're using a large sheet of material, something that's 4 by 8, like a large sheet of plywood, or 4 foot by 4 foot, will secure very easily with the vacuum system. When we get down to smaller sizes like 2 by 2 or smaller, we may need to look at additional ways of securing those parts. If we look at the video on the right here, this will demonstrate the process of the vacuum drawing a sheet of material down to the table. So if you look closely as the video runs, you'll see this gap get sucked down to the table. You'll hear the the vacuum system turn on, ramp up, and as it gets up to full speed, you'll watch the material draw down. And so now you can see that it's sitting flat on the table, and so that vacuum system runs the entire time that we're cutting. Again, if your material is too small, or if it's very warped, or maybe if the spoil board is too dirty or uneven, things may not want to draw down that well with the vacuum, and so we may need to look at other means of securing your parts. So if we look at this GIF, this is showing just a sort of step-by-step process for securing small parts to the spoil board. So the staff will help you come up with a plan to do this, and actually executing that plan. We'll go through that with you. This is something that we call the corner jig method, and essentially we have our part here, and on the left side and the bottom of the table we just have some scrap wood strips. We keep a bunch of pre-cut strips down at the CNC machines, so we use these to help clamp parts down. These other little egg-shaped things are called cams, and so the wood strips get attached with screws to the spoil board, and then the cams get attached with screws to the spoil board. But then as these cams rotate, they exert lateral pressure, and that's going to clamp the part between the cam and the scrap. So there's one on the right side to clamp to the scrap piece on the left, and one on the top to clamp against the scrap piece on the bottom. And using those things, we can secure most smaller parts pretty well. Okay, and now we're going to see a short video of the whole process start to finish. So we'll start with the machine measuring the tools, and then running through some of the 2-axis operations that we can do. So this is sped up, but here I'm attaching the strips and the cams to secure our small part. Now the machine is measuring out the tools. And so we just sort of watch it run. We can see some of our lettering getting cut out, and then our overall part getting cut out. Now we'll just clean up and remove the parts. So while your file is running, a trained person who is familiar with the project must be present at all times. So if you're working in a group, you can have group members sort of cycle through watching the machines. And while you don't have to pay for the time, you do have to actually be present. It's important that you're familiar with the project, because you need to look out for potential problems, and if you're not familiar with the project, then it becomes very hard to look to see if something's wrong. While you're watching the file, you must have safety glasses on at all times, and hearing protection. You really need to be attentive the entire time. You can bring your computer and other work to work on while you're watching the machines, but you really need to be regularly looking at the machine and listening for potential issues. Some of the issues that can occur, parts can become loose and actually get flung off the machine altogether. They might start to move, and then the quality of your parts is going to be affected. If they move, they could potentially lift up and collide with parts of the machine that they shouldn't. You may have a great amount of dust accumulation or wood chips that we might want to stop and clean the machine off periodically if you have a really large file. And because the router spins at a really high rate of speed, there's always a risk of smoke or fire if the router were to sit in one place for too long. If you were to experience any of those issues, you will stop the machine by just hitting the escape key on the keyboard at the main control computer. And there's also a big red e-stop button, emergency stop, on the control station, similar to some of the red emergency stops we have in the shop. A staff person will go through this with you every time we set you up at the machine. We will also probably give you some specifics, things specific to your job that might be of concern, and we'll go over those things with you before we start the file so that you know what to look out for and where potential problems may occur. I've mentioned a few times now that we need to look out for potential collisions. Quickly, we looked at the dust boot. So there are potential collisions with the dust boot that we need to try to avoid if your material is very tall or if the slopes in your model are very steep. Or they're not oriented in the correct way. The dust boot may be at risk of colliding, and so that's something we'll look out for when we're setting up your file with you and discuss with you when we start the machine. One of the most common misunderstandings that we see that can lead to collisions if they're overlooked is related to the image here, which I'm going to talk about tool lengths. So in this image, I have 4 different tool assemblies. So the top part of the tool is just what the router motor grabs onto to pick up and return the tools. The bottom half is the collet, and this specifically what we're looking at is the collet nut, which tightens the tool down to the upper part of the tool. And so these are the actual cutting tools down here. And so from left to right, we have a 1/2 inch, 3/8, 1/4 inch, and 1/8 inch cutting tool. And what you can see is that as the diameters get smaller, they get shorter. And in the background here, we have a glue up of plywood. So this is 3 layers of 3/4 inch plywood, so it's about 2 1/4 inches worth of material. And so what we see a lot of is people set out to make a site model of New York City, and their buildings are 2.5 or 3 inches tall, and they want to use this tool to cut out around them because their buildings are only an 1/8 inch apart. But the problem with that is that the 1/8 inch tool is only a 1/2 inch long, so we wouldn't be able to get that level of detail. And if we tried to cut lower than a 1/2 inch, you can see here that this top black part of the tool would start to rub in to the material and burn. And so we have to look very carefully at which tool we're using and how deep we're ultimately trying to cut. So for the wood in this picture, the only tool that we could use to cut out that piece of wood is the 1/2 inch tool, and so that's going to limit the level of detail that we can get out of that material. As I mentioned before, there's potential risk for collisions with other parts of the machine, especially if material becomes loose or starts to shift around while we're cutting. And so that's something else that we would talk to you about when we set up your file. I just wanted to talk a little bit about what CNC means. So CNC is an acronym for Computer Numerical Control. And a lot of different machines use this technology. And in fact, all of the laser cutters and the 3D printers in the lab are types of CNC equipment. They all have a controller that's outputting numerical data to servo motors that are and other types of equipment that determine the motions of the machine and the firing of the laser beams or the extruding of plastic or depositing of a material. So all of that is in a code file somewhere that's getting sent from the controller to the machine. And those coded languages can all be slightly different, but the generic term for them is G-code. When we create G-code for controlling the CNC routers, we call that process programming. So when preparing your file, the first thing you should do is meet with a lab tech to determine the feasibility of your project. If you've never used a machine before, especially, just stop by early on and talk to us, and we can sort of quickly give you the next steps and tell you whether or not what you want to do is possible. Once we determine that your project is possible, you can prepare a digital file and make an appointment to meet with us. So we would need you to draw out any curves or objects that you're planning to cut out or carve out of the material, and then make an appointment with us to look at that file and start to program your file. So once the program, so the staff will work with you to do the programming or help instruct you on doing your own programming. Once the program is finalized, we'd give you the go-ahead to maybe go glue up your material. And then often your material is going to have to dry for a day before it's ready to cut. Once your material's all glued up and your file is ready, we keep a physical queue of people that are waiting to use the machines. That queue usually can be a day or two wait time to get through it. Sometimes it can be the same day, but especially during big deadlines, you should expect to wait 3, 4, maybe 5 days from the time that we add you to the queue before you actually get to use the machine. But once a machine does become available, we would usually contact you either via text or email and set up a time when you're available to go start the machine and have you watch it run. So some things can add to the time that it takes to prepare, set up, and ultimately run your file. Some of the factors that increase the complexity of a file Small parts spaced close together. If you're cutting a lot of small parts out of a sheet of material, eventually the vacuum, as you cut the whole sheet, the vacuum may not be as effective, and you may see parts start to fall off the table. So it may require that we have a plan to manually secure those parts during the process. So developing that plan can take a little longer. We may need to run some tests. And then the actual running of the file could take a little longer because we would need to stop the machine and manually fasten the parts. Really small material that's not easily secured, we may need to again do some testing with you. We may need you to help us by building an actual jig that's going to secure the parts. So that can, really small parts could increase the time. And then parts that need to be flipped or milled on 2 or more sides. To do this accurately requires a certain process. It also can lead to unknowns, issues of stability. When you flip things over, they might not be supported from underneath, so we may need to make a support cradle. Again, this might require some testing be done in advance. So as you look to possibly flipping things, you would just want to keep in mind that that can be more time consuming, can take longer for you to ultimately get onto the machines. So we program our CNC routers using a software called RhinoCam. That's a plugin for Rhino. So in the image here, you're looking at a screenshot of Rhino with the RhinoCam running on the left toolbar there. So all files must be created or imported into Rhino before we can start programming. And so when you make your appointment, what we require is that you have this, at least have this file completed before you meet with us. And if you've never used a machine before, we can, in that appointment, go over how we would start to program your file with you, and just talk about all those details. If you're going to be using the mill frequently, we really encourage you to learn as much of the process as you want. So if you're doing your own programming, we can check that much quicker, especially as you get better at it. We also can start to walk you through some of the process of the setup of the machine and running the machine on your own if you're really going to be using the machines week in and week out. We encourage you to do that. So programming in Rhino can be divided into 2 main categories. So there's 2-axis and 3-axis operations. So this image shows a little sample board that we have up in the lab, and it just outlines each of those different operations. So you can see there's a facing, pocketing, profiling, and engraving. We can also drill holes or cut out shapes, but essentially we need 2-dimensional lines or points drawn out in our file to start the programming process. If we look at 3-axis operations, so again there's another little sample that we have in the lab. So this shows you some of the 3-axis operations. We have a horizontal roughing, a parallel finishing, horizontal finishing, and projection pocketing. So with 3-axis operations, the setup is going to require one, that we model our stock material, that we have a box or boxes in Rhino that represent the dimensions of the material that we're going to cut. It also requires that we have curves to identify the different areas within that material where we want to do some cutting. And within those curves, within those areas, some three-dimensional geometry, so 3D modeled geometry that we're going to carve out of that material. So in the file setup, that's what's going to be required for 3-axis is the additional modeling of the stock, as well as a 3D model of some kind. Okay, that wraps up the orientation. The next video will start to get into some of the 2-axis programming. Thanks.